and see what happens. Okay, we are live.
Okay.
16
Super,
watching.
We'll hang out for a minute.
Live.
Okay. Okay, we'll get started in just a moment. Okay, so thank you all for tuning into the final project demonstration for Engines 146, Computer-Aided Mechanical Engineering Design. I'm Professor Diamond, the lead instructor for this Dartmouth Engineering course, but I did not teach it alone. The class was supported by an extraordinary instructional team, and I encourage you all to read the biographies of the instructional team on the About tab of the course website. We have 30 students enrolled in the class. They are Dartmouth seniors or in their 5th year their BE program. For the class project, we've got 6 teams of 5 students who've collectively built 30 completed clocks in 6 unique designs. To keep this live stream event manageable, we're going to be demonstrating today one representative clock from each team. Today's project, the class project, was inspired by the development of the marine chronometer as a solution to the longitude navigation problem of the 1700s, combined with the exciting technological progress in affordable desktop 3D printing of today. While researching this project, we did find that there are examples of 3D printable clocks on the internet, but the level of attention that we are applying to the accuracy, the precision, and the duration capabilities of these clocks has brought the challenge to a higher level. Also, we couldn't find any examples of 3D printed clocks specifically designed and tested to reject motion disturbances like a marine chronometer, as the students have done in this class. So making a high-performance 3D printed clock with a desktop 3D printer is not an easy task. The students needed first to statistically characterize, to troubleshoot, optimize, and document the geometric accuracy and precision performance of their 3D printers. They modeled and tested complex mechanical components from scratch. For example, the involute gear tooth profiles were modeled, printed, and tested in the fidget spinner exercise that you can also examine on our webpage. Implementation of gear trains in the clocks is necessary to extend the duration of the clock operation. But students had to fight frictional losses in the bearings and the meshing of the gears. with teams relying on 3D printed springs for energy storage, by and large. The understanding of non-ideal elastic properties of the PLA polylactic acid filament was also critical. The balance wheel hairspring subassemblies are harmonic oscillators in these clocks with periods that were fine-tuned based on adjusting the moment of inertia and spring constants. And executing a highly technical engineering project with remote collaboration added additional challenges. When compounded by an extremely compressed timeline, a carefully choreographed design and execution process became essential. We formed teams on April 21st, 2020. That's just over 6 weeks ago. And what you're seeing today is not a first draft. In fact, you're seeing the third revisions of these clocks soon on your screens today. So without further ado, we're going to give you a tour of the clocks that the student teams designed. We're going to shift the video spotlight to each team in turn, so you can see and hear a brief description of the clock design and the team's design process. And after all 6 teams have been introduced, then we will proceed with the competition. So let's spotlight on group 1.
All right, so we have our clock. We went with more, when we were doing research, we found online a lot of these clocks were laid out in a horizontal manner. And because to fit along more with the theme of marine chronometers, we saw that a lot of them were very cylindrical based. And we also thought that a cylindrical based clock would look nicer on a desk. So that is how we went with our design. So we have our hairspring here on the bottom, which you can see, our pallet and escapement gear on the next layer, and 2 gearboxes, which gave us 25 gear reduction. And at the top, we have our mainspring, and we have our encoder wheel with our encoder mounted right there. And yeah, so we wanted everything to be nice and compact and layered, and which made it easier for us to test because all of these separate layers are different modules that we could build and design isolated, knowing the dimensions that would fit for the next one on top and the ones below. Therefore, we could expedite the entire design process and print process because we would all be working on individual models. And then once we got that working, we can print out one of our teammates' models and then it will fit right in perfectly.
Wonderful. Thank you, Juan. Let's go to group 2.
Hi, so this is our clock here. And although we were allowed to use fasteners and bearings, our group decided to go after a challenge to design all of our parts out of 3D printed material. So the clock that you see here was entirely made out of PLA parts and designed through the 3D Experience platform. Some high level design inspiration was that we wanted to model our clock after a boat to emphasize the history, purpose, and kind of the oceanic theme of the marine chronometer project. So some ways that we did this was that the balance wheel is modeled to look like a steering wheel on a ship. We put a lighthouse on the front of the clock, and you can see here the base of the chassis was modeled to look like a boat with a raft mounting the encoder. So just fun ways that we could incorporate the oceanic theme into our design.
Thank you. And let's go to group 3.
All right. Hello, everyone. Yeah, we're group 3, and this is our chronometer design. Really early on in the design process, we decided that we wanted to use a pendulum as our timekeeping mechanism. And that was really for the sake of uniqueness. And because we use the pendulum, we decided to model our clock after a grandfather clock. And so, you know, if you think about it, with the free swinging pendulum, eventually it would slow down and ultimately come to a complete stop, and along the way not have a constant period. And that's due to energy losses within the system, primarily frictional energy losses. And so in order to keep our pendulum to keep ticking, we also had to design a power subsystem. And so Jack and Cole were responsible for that subsystem. It actually features a really cool track system. So pretty much there's a falling weight, and that falling weight is connected to the pendulum via the escapement. And as that weight falls and through the escapement, it provides little nudges and impulses that keep the pendulum swinging. And then the track system is used to keep the falling mass in place. And so it can only move in the Z-axis. And, you know, and that was a huge design challenge because the clock has to be able to operate on a moving print bed. So stabilizing that falling mass and also stabilizing the pendulum took a lot of work, but ultimately we're pretty happy with how it performs. And then Julian, Evan, and I, we designed the escapement subsystem and configured the pendulum so that its timekeeping ability wouldn't be affected by the moving print bed. And you know, the goal was for the pendulum to hit a 1,000 millisecond period, and currently we're hitting a 950 millisecond period. So we're pretty close to on the mark, and we're pretty happy with how it turned out. And then finally, Evan also, you know, made our clock actually, you know, incorporate some features from an antique grandfather clock by designing that really nice lattice work that you see on the front. Yeah, and that's pretty much what we got. And just want to say thanks to everyone for tuning in. And Group 3 had a ton of fun making this clock work and working together. So thank you, everyone.
Wonderful. Let's go to Group 4.
Hi guys, we're Group 4. We went with a fun fish theme for this marine chronometer. Our primary design goal was just to build a functioning clock, but we were focusing on precision and accuracy. So that was sort of driving our decisions. And the way that our team ended up splitting things up was in the very beginning, we had each teammate be in charge of a sub-assembly and sort of become an expert on that area. And so each individual sort of made up their own design constraints and their own design intent. And then as the weeks went on, we started putting things together and collaborating a lot more. So we'll have each person kind of talk a little bit about their own assembly.
Yeah, so I was responsible for the mainspring, and the mainspring is basically the powerhouse of the clock. And one of our main design goals was to have it run for 45 seconds to 1 minute. And in order to do that, we decided to design a thick, large spring to store as much energy as possible. And ultimately, our design was able to provide enough power to run for 2 to 4 minutes.
I was in charge of taking care of the gear train, and I think the gear train was the part of the design that was sort of like initially very much informed by theory, but then as we prototyped early and very often, we discovered that due to some things that were unpredictable, like power output and nature of product that we were working with in terms of the plastic we were printing, there were a lot of things that we could change with the gear train to optimize length of pulse, and ultimately that ended up being what guided the final gear train design.
Hi, I'm Mikey. I was in charge of the escapement. So the escapement takes all that energy that the gear train brings us from the mainspring and meters it out slowly with the help of the balance wheel so that everything doesn't just unwind super fast. And reducing frictional losses there and making sure you have a really precise knocks to add that power is super essential.
I was in charge of the balance assembly, and for the balance assembly, the hairspring and balance wheel don't have too much room for design change. So there's mostly a lot of iterating upon different spring designs, and eventually we were able to tune it down to control the ticks to about a 999 to 1001 millisecond period.
Yeah, and lastly, we had to put all of that together on a chassis. And so our main goal with that was just making everything super modular so we could put everything together and kind of tune on the fly as we wanted to. So we're able to kind of overcome a lot of our printer tolerances by designing our chassis in a way that let us slide our test rigs the way we wanted to. And ultimately, this is our clock, and we're super happy with it.
Wonderful. Let's go to Group 5.
Hi, so this is our clock. One thing that we focused on, as you can see, is kind of the horizontal layout of the clock, because we wanted, we thought at the beginning of the term, and we kind of got introduced to the idea of kind of just the general clock and each of the individual mechanisms and components. We wanted to be able to kind of showcase each component as much as possible, because we just thought it was really cool to have all the components working together. And so as you can see, we have the power of the mainspring on the left, or on the right side of the screen, actually. And that is attached to the gear train and the escapement mechanism, and then on the far left to the balance wheel and hairspring. And at the beginning of the term, we also split up into, like Team 4, we split up into different groups so that one person took charge of each subcomponent. And then we put one other person as kind of a secondary on each of those subcomponents. So we had like an expert and then somebody they could collaborate with who was working on other components, who could offer different perspectives on that component. And it was definitely kind of enlightening to have both the expert and somebody that they could collaborate with, which is kind of showcased in the escapement mechanism in particular. We had been focusing on one escapement design, but as we were working with the balance wheel and the escapement, those two components on the left side of the screen there, they really are intertwined. And so kind of in the last iteration of the clock, we kind of changed the whole escapement mechanism, and it really improved the accuracy, the precision of our clock and the accuracy. And we were able to get it within about a 5% accuracy to about like 950 to 1,050 ticks per second period. And it was just, yeah, it was a great experience to kind of iterate on these designs throughout the term. Our clock changed a lot from that first iteration, and we definitely learned a lot. And I feel like I learned a lot. I worked on the mainspring, and it was very enlightening to kind of iterate on that and get that part to work, particularly in context of the other components.
Thank you. And let's lastly go to group 6.
All right, for our clock, our main design goal here was to have the longest running clock, which really helped us focus on some specific components which we wanted to optimize. So after making our original clock, we just used that to test like how long does it run and what can we do to improve it. And a few areas of improvement included the gear train. We originally wanted to do a 25-to-1 ratio, gearing ratio from the mainspring there to the escapement, but we ended up going to 18-to-1 because the added power bonus of that 18-to-1 gear ratio actually made it longer, even though the mainspring unwound faster. Other components include the escapement mechanism. We originally wanted to go with a standard gram escapement, which is very simple. However, there's a lot of friction in a gram escapement because the pallet fork is always making contact with the escapement. So instead, we designed a much more complex club tooth escapement. And this way, we reduced a lot of friction that we encountered when the pallet fork was running. And finally, optimizing the hairspring to continue ticking. There's a fine line between speed, as in it'll make the escapement wheel unwind faster, and power, the amount of power that the mainspring has to input back into the pallet fork to input it back into the hairspring to keep it running. There's a balance between those two things, and we really had to optimize that hairspring to reach that balance. In the end, some of our clocks could run up to 5 minutes on testing, though they weren't as accurate, which is why here our final design only runs for maybe 2 minutes. However, it's accurate to generally within 50 milliseconds, 950 to 1,050 milliseconds.
Okay, well, thanks very much. So that's a tour of the representative clocks from each group. And now as the students ready their clocks with this custom G code that runs the print bed forward and back to simulate the undulation of a seafaring ship, let me orient you to the viewers to the live stream dashboard. So once we begin, we're going to spotlight the various clocks while in operation. And meanwhile, the scores, which are being read out through these optical encoders and their Arduinos, are going to be updating automatically on the dashboard that's directly above the live stream video feed on the website. So those scores that you see combine the precision, or how regularly the clocks tick, with the duration of the clock operation. And the group with the highest score at the end is the winner. So when the clocks are ready, please give me a signal on the teams. Please give me a ready signal, and I know that we're ready to start. All right, looks like we are all ready. Set. Start your clocks. So the bed movement starts off with a gentle oscillation, and there are some storms, though, that occur in the code. So it's going to go through some different types of movement profiles. So at this point, you should begin to see the scores coming through on the dashboard. So each of these designs is unique.
All right, ours stopped.
All right. There is some delay as the scores propagate through the internet to the dashboard. So it can take up to 30 seconds for that to propagate through. We still have 5 clocks running.
No, mine stopped a while ago.
Okay. 4 clocks running.
Mine stopped too.
3 clocks running.
Mine has gotten back to going, but I've stopped the processing.
My group 6 has stopped.
Group 3 has stopped.
Group 4 is in a storm.
Looks like the storm may have passed. It's still ticking. Looks like storm is taking place on group 5's printer there.
I'm just letting it run at this point.
Yep. Group 4, are you still ticking there?
We're still ticking.
Still ticking. Anyone else still ticking? Group 4 is still going.
Looks like we're done.
And you're done. Okay. Fantastic. So looking at the scoreboard, looks like group 4 took our lead position, and followed up by groups 3, 6, and then 2, 5, and 1. So I'd like to thank everyone for tuning in to this demonstration, and I'd like to give special thanks to all of the students in Engines 146 for sharing their work and sharing their process in today's live stream demo. I really appreciate your willingness to showcase the great work that you've done in Engines 146. And we hope that all of you in the audience have enjoyed the show. The Thayer School Communications Office is preparing an offline video of this event. That'll be shared in a few weeks. And that's a wrap, everyone. So goodbye.